Now, we're going to take a look at a process for finding the integral of these functions that have been composed. Okay. The functions that have an inside function that's not just an x. All right, so there's a process that we can use, and I'll try to be consistent in the use of that. And then you can be the one to make the decision about whether you want to try it with just pattern recognition. Okay, I will caution you that pattern recognition works really well when you see right here, that negative 8x is the derivative of the inside. Or right there, the 2x was the derivative of the inside function. Those are the ones where pattern recognition works great. I always have students that want to do the pattern recognition on the ones that aren't so clean cut, and it can sometimes cause a problem because they get their constants wrong. So if you're going to do pattern recognition for this, you really need to check your answers by taking the derivative. You really need to do that if you're going to be using pattern recognition. All right, so when you're doing these, the first thing that'll help is to get that rewritten so that it looks like a power function. And so that in the denominator then could have been moved up to the top, and when it does, it would be 1 minus 2x squared, that quantity, to the negative 2 power, and then that negative 4x dx. I'm going to just write over here to the side. So here's the formal process we're going to wind up using. It's called use substitution sometimes, or just change of variables. So what we're going to do is try to simplify the look of this by letting u represent this inside function. So if I let u equal 1 minus 2x squared, I can do the derivative of u with respect to x, and I would just get negative 4x. Now I'm going to write that in differential form by multiplying both sides by dx, and I get negative 4x dx. Then what I'm going to do is I'm going to come back to the original problem I was doing, and right here, okay, where I see the 1 minus 2x squared, I'm going to replace it. See, 1 minus 2x squared, I can replace it with a u. And this negative 4x dx is exactly what I want. Okay, I can replace it with du. So what I have is u to the negative 2. Then I have this getting replaced with du. And what I can do is just think about how to integrate that. And so I know that would have been u. Add 1 would have been negative 1. The negative 1 would have come down in front, so I want that not to happen. So I'm going to do the little negative on that. I'm going to throw a plus c on it. But then I don't want my final answer to be in terms of u. That was an artificial thing that I did. I put the u in to make it easier to think about. So what I'm going to do is replace the u now with the 1 minus 2x squared. Don't want to have negative exponents. So that negative 1 right there means I really have 1 over 1 minus 2x squared to the first power. So I don't even need to write to the first power. Don't forget the plus c, and there's your answer. Now, once you rewrote it so that it was a power function, once you bring that 1 minus 2x squared to the second power up, you could have done this one pretty well using pattern recognition, since right here, this right here, was the derivative of the inside function. But I'm trying to emphasize this process. I want you to have this security that there's a set process that you can use that's going to work for you. Okay? Make a note to yourself right in here that you need to be sure to get back to x's. Don't leave it with a u. Okay? All right, so let's go ahead and do several more examples of this. Sometimes they'll be nice. Sometimes we'll have to do some kind of an adjustment because we might not have a constant that we need. All right, so as I'm looking at question number 6, I like what I see. Because if I think about this being my inside function, I can see where the t to the third would have come from. The derivative of the inside would have been 4t to the third. Now, no worries about the fact the constant that I want is not there. Watch how we can handle this. Okay. So what I can do is first think about this one. Let me make that a little skinnier. Okay. We can first think about this as having that t to the fourth plus 5 is raised to the 1/2 power. I'm going to have that t to the third next to that dt because you'll see what's going to happen in a minute. I haven't done any kind of integral yet. I was just trying to get it to look like a power function. So if I'm going to use u substitution, I'm now going to look at that, and I'm going to let u be the thing that's under the radical, because it's what's being raised to a power. I'm going to do the derivative of that with respect to x, which is 4t to the third. Derivative of 5 would have been 0. Oops, and it's a t, so that should have been dt rather than dx. And I'll move that dt over. I'll put this in differential form. And then what I'm going to look at, this is what I like to do, is I'm trying to make substitutions over here and get the t's to be replaced with u's. So I'm noticing the t to the third dt, oops, that's too thick also. Let me get that thinner, and let me try that again. Okay, so I'm noticing that right there, and I see that right there, but I don't have the 4 over in the problem I'm trying to work, where I got a 4 here. So can't I get rid of that 4 by multiplying by 1/4 on both sides? Wouldn't that get rid of it? So I can isolate this. Because what I'm trying to do is get u's into the mix. So now I can replace that with a u. It's raised to the 1/2 power. The t to the third dt, the equal sign tells me it's equal to 1/4 du. Okay. And then that 1/4 is really a constant. I normally like my constants to be in front, and I'll get to where I just write it there. I don't automatically put it with the du. But that's what I'm trying to integrate now. So I can forget all about the messy looking problem and just think, okay, so I'm going to need to, now I'm integrating. Let me change color since I'm actually now doing it. I'm going to add 1 and get 3/2. I would need a 2/3 out in front for that 3/2 to cancel out. The 1/4 was already there, so don't forget about bringing it down. Okay. Put a plus c on it, because you could have had any constant there. Simplify, and that's going to wind up being 1/6. Okay. And the u to the 3/2, that's the same as a square root of u raised to the third. You could have the 1/6 out in front, or you could have the 1/6 underneath. Either way, you're not quite done, because you have u's, but you need you need to get the t's back in. So that's when I'm going to go back and make this substitution. All right. So in place of the u, I'm going to put back in there the t to the fourth plus 5. It's cubed. And I could leave it like that. I could have had that raised to the third power. I could have had it on just the t to the fourth plus 5 inside here instead. Okay, so there's variations like that you might see. If I have to evaluate it later, I like it that way. Okay. And then you could also see it where all of this is on top. all over 6. That's no better or worse. These are okay. Both of those are okay either way. So there's going to be a set process that you can use that'll help when you don't quite have what you really want outside here. Like I would have really liked to have had a 4t to the third, but I didn't. Okay. But that was okay because I can always manipulate the constants to get them to be what I want. And I can do this using pattern recognition. But I thought I would just let you get comfortable with that idea that there's just a process that you can use that's going to work. Okay, so let's try this one. Okay, so looking at this one, that x to the third came from the derivative of 1 plus x to the fourth. Of course, it would have had a 4 on it, but that's no worry. That's just a constant that I can deal with. So I'm going to rewrite this first to bring that 1 plus x to the fourth. That quantity would have been to the negative 2 power. And then I can think about that x to the third over there with the dx. So I'm going to let u equal that 1 plus x to the fourth. And I'm going to take a moment to do the derivative of u with respect to x, and then bring that dx over and get that written in differential form. All right, now here's the x to the third dx. Ooh, I don't have a 4 right here, but I could multiply both sides by 1/4 and get rid of that so that I have what I need. I'm not dividing, that's just dividing by, oops, should have been a plus. All right, let me say that again. So I just divided by 4 or multiplied by 1/4. And I did that because I want this to match that x to the third dx. Because I'm going to now replace the 1 plus x to the fourth with u, and the x to the third dx with 1/4 du. I'm going to keep the 1/4. That's just a constant out in front. By the way, you can bring it all the way out in front, but I usually just carry it along, so I don't really worry too much about that. And at this point, I'm going to start doing the integral, the antiderivative. So the u to the negative 2 would have come from a u to the negative 1. But I'd need a negative out in front, and I had that 1/4 that needs to be carried along. So checking that, do you see how that negative 1 times the negative 1/4 would be 1/4? Then you'd subtract 1 and get u to the negative 2. All right, so that looks pretty good right there. Okay. All right, I'm going to put a plus c on it. But I'm not finished because I need to get x's back in there. And it's also not okay to leave that negative exponent. So you might take and move that down to the denominator right now, and then go ahead and replace your u with the 1 plus x to the fourth. Okay. Don't forget the plus c, and that should do it. Feel free to check that by just taking the derivative and making sure that when you do the derivative that it matches this part right here. Okay. All right, let's see what else. All right, I'm going to try to do these other two in this video. All right, so on this one, we'll rewrite. We'll put the 5 minus 2x in parentheses, and then it's being raised to the 1/2 power, really. Now, the derivative of the inside here would have been a negative 2, which is just a constant, so that I can always manipulate my constants to be whatever they need to be. So I'm going to let u equal the 5 minus 2x, that inside piece. Then du dx would equal negative 2. Let's write it in differential form. By the way, it's okay when you're ready to just write it, always write it in differential form from the start. And then when I go to make my substitutions, I know right here I can put a u, but I don't see the -2. So I want to be able to replace the dx and know what it's equal to. So if I multiplied by -1/2 on both sides, that would get rid of that -2. And there's that dx that I wanted to be able to plug in. To replace, I want to replace the dx. So that means here I can put a u. Here I can put a -1/2 du. And it's easier to integrate when you have your constant and then that u to the 1/2 with the du there at the end. All of that's just that change of variables part, just that rewrite part. Okay. All right, so now I'm going to think about this, and I realized that the 1/2 would have had to come from a 3/2. I'm going to go ahead and just make that cancel out, but make sure I bring that constant along that was already there, that -1/2. Put a plus c on it. You're basically done. Now all you got to do is clean up, which would be a -1/3. Replace the u. I'm looking back here at how u was 5 minus 2x. It's being raised to the 3/2 power. And then I noticed that the original, or remember I should say, the original was a radical. So I want to get back into radicals. And it would have been a square root because of the 2 on the bottom. And then this quantity would have been cubed. Okay. Now I could write it that way. Or I could put this over the 3 and have the negative maybe right on that line out in front. So be flexible about that when you're checking your answers. You might just be right, even if it looks slightly different than what you're seeing in the back of the book. All right, let's do one more where there is a constant, but not the one I want, that 5. Okay, I'm going to let u be the inside function. The derivative with respect to x of that would have been 3x squared plus 0. The differential form would be 3x squared dx. Now when I'm looking at this, I see the x squared dx, but I don't like that 5. I have a 3 when I did it. So in both instances, it's not quite what I want. So think about how that 5 can just go along for the ride. How this x to the 3rd plus 5 raised to the 6th power is sitting there. And then that x squared dx. So I see the x squared dx. I'd like to replace it with something involving a u. And what I notice is that 1/3 du would equal x squared dx. I can get rid of that 3 by dividing by 3 or multiplying by 1/3. So then this can be replaced with 1/3 du. The x to the 3rd plus 5 is what I was calling u. And the 5 was part of the original problem to start with. Okay. So I would like to reorganize my constants and put them both in front. And then that constant I'm just going to bring along while I ponder the u to the 6th. But doesn't it come from u to the 7th? But the 7 I'd want to cancel out, so I'll bring a 1/7 out in front. Don't forget the plus c. Also, don't forget that you've got to clean this up a little bit. So that's 5/21. And I don't want u, I want x's. So I got to replace it with an x. And then that's a pretty good final answer right there. Only thing you could potentially see different is that they put the 21 underneath everything.